Hello everyone, my name is Tyler Hassett and I'm here to do a demonstration on using the Bernoulli equation to solve a fluid mechanics problem. So here's our agenda for today. We'll start with a brief history on the Bernoulli equation, then we'll break it down. We'll go into some conceptual examples, then we'll talk about why it's important and why we should learn about it, and lastly we'll go through 2 example problems. Does everyone have a handout just to start? So, history. Pictured on the right is Daniel Bernoulli, who was a Swiss mathematician in the early 1700s, and he did a lot of research on animals and questioned how the speed at which blood flows was related to its pressure. And in 1738, he published a book called Hydrodynamica. In this book, he came up with an equation that relates pressure to velocity. The equation states that 1/2 times the density of the fluid times the velocity squared plus its pressure equals a constant number. This means that if the velocity of a fluid increases, the pressure has to decrease, or if the pressure increases, the velocity has to decrease. This is based off of the conservation of energy. The same way that a body transfers kinetic energy to potential energy, a fluid transfers kinetic energy to pressure. So today, Bernoulli's equation now takes into account potential energy as well. And there's 2 different forms. One I'll call the pressure equation, the other one I'll call the head equation. In the pressure equation, we have the pressure of the fluid plus the specific weight times the elevation plus the density times the velocity squared over 2 equals and the specific weight of a fluid is just the density times the gravitational constant. The head equation is the equation that we're going to use today, and it says that the pressure divided by the specific weight plus the elevation plus the velocity squared over 2 times the gravitational constant equals a constant number. Now the units for the pressure equation are PSI for the English system and newtons per meter squared for the metric system. And for the head equation, the units are feet and meters. So in order to use the Bernoulli equation, we need to make 4 assumptions. First off, it needs to be an incompressible fluid, which means the density doesn't change. Next, it has to be steady flow, which means the total amount of flow over time doesn't change. Third, the points that we need to compare have to be along the same streamline. So in the picture on the right, you can see the air moving over the car in streamlines. So it's only fair to compare different points along one of those streamlines. And lastly, the flow needs to be frictionless. So now we know the relationship between pressure and velocity. We can look at some conceptual examples. On the left is a picture of a wing. You can see how air is moving over the top of the wing and beneath the wing. The air moving on top is moving at a higher velocity, which means it has lower pressure. On the bottom is a lower velocity, which means higher pressure. And the difference in pressure creates a lift force that allows the plane to actually fly through the air. Next, we'll do a quick little experiment called the 2-ball experiment. I'm going to blow air through between these 2 balls, and we're going to see if the balls come together or move apart. So you can see as I was blowing air, the balls actually move together. This is because the velocity of the air between the balls is much higher than the air on the outside of the balls. High velocity means low pressure, and low velocity on the outside means high pressure, causing a force to push the balls together. So some of you may be asking, why is this equation important? Well, it allows us to do many different things. First, it allows us to measure pressure drops in piping. It allows us to measure the velocity of a fluid. It's the concept that allows airplanes to fly, which we already talked about. It's also the concept that allows a pitcher to throw a curveball. As the ball spins, it changes the difference in velocity of the airs on the outside, creates a force that allows the ball to drop. And lastly, it's used in safety. Here's a picture of a train station. You can see the yellow line. And the reason they have this yellow line isn't just because you don't want to stick your hand out and get hit by the train. It's because as the train comes by, the air in front of you is moving much faster than the air behind you. So it creates low pressure in front of you and high pressure behind you, pulling you into the train. So you want to stay, obviously you want to stay behind that yellow line. So now let's learn how to use this equation to solve a problem. It's a step-by-step process. First, you pick 2 points along a streamline. Then you write down your Bernoulli equation. Third, you make your simplifying assumptions. And when we go through the examples, I'll show you how to make those assumptions. And lastly, you compute your value. So here on the back side of the handout is example 1. and we have a pipe going up a hill, and the question is asking us to find the velocity at point 2. So first we pick our 2 points, point 1 and point 2, you have them on the red box up here. Then we write down our equation. And because these 2 points are along the same streamline, we know that both sides of the equation equal the same constant and therefore equal each other. So given in the problem is the velocity at point 1 is 5 meters per second, the pressure at point 1 is 600 kilopascals, and we're calling the elevation at point 1 0. The question says point 2 is open to the atmosphere at a height of 50 meters above point 1. Now here's where we can make one simplifying assumption. When something is open to the atmosphere, we can consider the pressure as 0 pressure because it's atmospheric pressure. So now we plug in our values into the equation, and we need everything in base units. So when something is 600 kilopascals, we need to make it 600,000 pascals, and a pascal is the same thing as a Newton per meter squared. So we plug in, and gamma, which is the specific weight, is gravity times the density, so we have that. V1 is 0 meters, because that's where we decided to call it 0 height. Plug in the velocity, and then on the other side of the equation, we know the pressure at point 2 is 0, because we made that assumption, because it's open to the atmosphere. 50 meters, because the point's 50 meters higher than the first point, and we're solving for V2. So subtracting, multiplying, and taking the square root, we find a velocity of 15.65 meters per second. All right, example 2. I'm going to write down the equation on the board so we can do it step by step here. So this question is asking us to find the velocity at a specific depth in this river. So you put in your L-shaped tube and measure how far the water comes up in that tube. So first we pick our 2 points, point 1 and point 2. Then we write down our equation right here. Again, they're along the same streamline, so both sides of the equation are equal to each other. Now we make our simplifying assumptions. Well, something special is about point 2. We know that at the top of this tube here, the velocity is 0. So therefore, at point 2, the velocity also has to be 0, and this is called the stagnation point. Also, we know that point 1 and point 2 are at the same elevation. So now we can start crossing things off on our equation. Z1 and Z2 are the same. We know V2 is 0 because of the stagnation point. And an equation to use in fluid mechanics is that the pressure is equal to the specific weight times the depth of the water. So at point 1, we know the depth of the water is 1 meter. So we have gamma times 1 meter over gamma plus V1 squared over 2G equals, and we know at P2 the depth of the water is 2 meters. So we have gamma times 2 meters over gamma. The gammas cancel out, and subtracting 1 to the other side, multiplying by 2G, and taking the square root, we get a velocity of 4.43 meters per second. So with that, I'd like to do a little recap here. We started with talking about the brief history of the Bernoulli equation. Then we went into why it's important, why we should study it. We talked about the problem-solving process, the 4-step process that allows us to compute a final answer. Then we went over 2 examples. If you want to find out more information, my contact information is on the bottom of the back side of the handout, as well as Professor Chin Wu, who teaches fluid mechanics class here at UW. He's a great guy, and he loves answering questions about fluid mechanics, so his contact information is there as well. With that, I'd like to take any questions. Yes, Professor Zwick.
Does it make any difference if it's fresh water or salt water?
The question was, does it make any difference if it's fresh water or salt water? The answer is yes, because those 2 different fluids have different specific weights and densities, so the values will change, but the process is still the same.
Okay.
Yes?
Does that equation apply for both turbulent and laminar flow, or only laminar?
The question is, does this equation apply to both turbulent and laminar flow? Well, here if I can draw a picture real quick. You have your pipe here. And so that when we're using this equation, we're assuming that the flow in the pipe is the same throughout the whole pipe. So it's moving this way at the same velocity. So we are making an assumption there. There's also another equation that you use coefficients in front of the velocity to take into account laminar versus turbulent. But yes, it does matter if it's laminar or turbulent, but this we're assuming that it's all the same velocity.
Okay, thank you very much.